Something unprecedented is happening. In September 2025, Earth is facing a wave of near collisions. Asteroid 2025 FA22 will pass by us at a distance twice that of the Moon, while 2295 RJ2 will come even closer, less than 300,000 kilometers. During one record-breaking week, many small objects at sublunar distances are recorded. At the same time, a chemically unusual interstellar visitor named 3I/ATLAS accelerates towards Mars on a trajectory unlike any recorded by the Center for Small Planets. The numbers contradict probability. Is it just a cosmic coincidence? Are we witnessing a pattern that could change the approach to protecting our planet? The answer could redefine what it means to be a standard in the solar system. September 2025 arrives with a continuous series of warnings. Astronomers at the Small Bodies Center are tracking the asteroid 2025 FA22 at a distance of just over 2.5 lunar distances, about 835,000 kilometers. 3 days earlier, 2025 RJ2 passed even closer, just 78 hundredths of a lunar distance or less than 300,000 kilometers. This is not an isolated event. The week from September 12th to 18th breaks all previous records. At least 28 near-Earth objects pass within the orbit of the Moon. This is 3 times more than the previous weekly record. Most of them are small, ranging from 8 to 25 meters, capable of burning up in the atmosphere or exploding like in Chelyabinsk. But 2, FA22 and RJ2, are large enough to attract the world's attention, with estimated diameters up to 120 meters. Each new discovery lights up on the screens of the observation team. Pan-STARRS in Hawaii, Atlas in Chile, Rubin Observatory in Atacama, Catalina in Arizona. Data comes from automated telescopes processed by software designed to capture even the faintest and fastest moving objects. The pace is relentless. New objects are marked, tracked, and recorded sometimes just hours after their discovery. The Rubin Observatory, just a few months fully operational, brings a stream of fresh data. Its wide-angle camera captures the sky, recording objects that might have gone unnoticed just a year ago. Statistically, this event should occur once a decade. Population models, adjusted for observational distortions, estimate the chances of seeing more than 25 sublunary objects in a week as less than 1 in 1,500. Even with the improved detection system, the September surge stands out, a cluster that does not match the usual random distribution of asteroid approaches. Some experts suggest orbital resonances or hidden destruction in the asteroid belt, but most point to the power of new technologies. Detection efficiency now exceeds 90% for objects larger than 20 meters within 1 lunar distance. Blind spots are diminishing, but not disappearing. Approaches from the sun remain a weak point, a lesson etched in memory after the Chelyabinsk explosion 12 years ago. In social networks, numbers give rise to speculation. Graphs circulate showing a sharp spike that seems too abrupt to be random. Some call it organized. Some suggest it was a warning shot. In scientific circles, the mood is more measured but no less wary. Every close passage is recorded, analyzed, and archived, feeding the planetary defense system, which is as strong as its last detection. For a brief moment, the world's attention turns to the sky, raising the question, what if one of these objects was aimed a little closer? Imagine if the FA22 hadn't missed. With a diameter of 120 meters, roughly the height of an urban block, the entrance of the asteroid would begin high above the atmosphere, a silent point racing at over 18 kilometers per second. If it were a Type C asteroid, like most objects of that size, it would compress the air in front of it until the pressure shattered it in a powerful air explosion, similar to what happened in Chelyabinsk in 2013, but scale matters. The shockwave from Chelyabinsk shattered windows in 6 cities and sent over 1,500 people to hospitals, mostly with cuts from glass and concussions. The FA22 carries more than 20 times that energy. An asteroid of Type C of this size could explode at an altitude of 10 to 20 kilometers, releasing energy equivalent to several megatons of TNT. The shockwave would flatten buildings over dozens of square kilometers. Everyone near the center of the explosion would have mere seconds to react. Glass would shatter, walls would bend, and the flash of heat could ignite roofs. The destruction would not be limited to just the point of entry. The surrounding areas would feel the impact, with flying debris and collapsing structures, worsening the danger. If the FA22 were made of iron, the situation would be different. Iron asteroids are denser and more cohesive. Instead of being destroyed, the iron body could pierce the atmosphere, striking the ground at nearly full speed. The result is a crater hundreds of meters wide, a fireball visible for miles, and a cloud of ejected particles rising into the stratosphere. A local strike would devastate infrastructure, but the ecological consequences could spread much further, depending on the impact site. Now imagine the target is in the ocean. More than 2/3 of potential impact sites are water. Here, energy transforms into a massive steam cloud and a series of tsunamis radiating outward. Although most of the wave energy quickly dissipates in the deep sea, coastal areas within hundreds of kilometers may face walls of water several meters high. Ports, cities, and low-lying islands will be threatened by a catastrophic flood without warning. An event in Chelyabinsk revealed a blind spot. Objects approaching from the sunny side are invisible to ground telescopes until the last moment. Sergei Karpov, whose dashcam video became a symbol of that morning, still describes the aftermath in terms of noise, glass, and confusion. Years later, he works with disaster response teams, urging cities to conduct drills for events that provide no warning. His message is simple. The line between a harmless fireball and a catastrophe capable of destroying a city is thinner than many realize. In simulations conducted after each close pass, the numbers look threatening. The energy of collision, population density, time of day. All these are variables in a cosmic equation unfolding without malice or intent. The only defense is vigilance, early detection, and systems that turn warnings into actions. Without them, the price is measured in ruined cities and forever changed lives. Comet Swan offers a spectacle of a different kind. It was discovered on September 11th, 2025, not through an optical telescope, but thanks to solar wind and esoteric methods. The device installed on the SOHO satellite detected her arrival when hydrogen emissions suddenly surged. The ultraviolet Lyman alpha signal, invisible to the naked eye, lit up in data streams before most ground observers even realized they needed to look. A small group of amateur astronomers studying the constellation Virgo confirmed what the satellites hinted at. Swan brightened rapidly, her tail doubled in size overnight. This was not just a matter of brightness. Spectroscopy showed that the comet's coma is full of volatile substances, predominantly hydrogen, and small amounts of cyanogen and carbon compounds. The ejection speed sharply increased as the comet approached perihelion, with hydrogen production surpassing water vapor emissions to such an extent that even experienced observers were baffled. The reason? The icy core of Swan was breaking down under the influence of sunlight, revealing fresh layers and releasing trapped volatile substances in a series of eruptions. Each new crack in the core signified a new release of hydrogen, visible to instruments tuned to ultraviolet light. Professional observatories hurried to organize subsequent observations. The Rubin Observatory, still adjusting its observation schedule, allocated emergency time to track the developing coma. Meanwhile, cities and scientists continued to transmit data to the system, recording emissions, mapping the morphology of the tail, and noting sudden changes in brightness. Their signals helped guide high-resolution spectrographs to capture fleeting details. Streams of material erupting from the core, subtle changes in chemical composition, and characteristic signs of structural stress that often precede destruction. As September approaches, the risk of fragmentation has become particularly relevant. Recent models indicated that the Swan core, already riddled with cracks, may not survive a close approach to the sun. If it disintegrates, the resulting cloud of debris could create a stunning spectacle visible from both Earth and space. For the planetary defense teams, Swan's unpredictable behavior served as a reminder that not all threats follow quiet, predictable paths. Sometimes a warning comes in the form of a sudden hydrogen release, and the first line of detection is a global network of enthusiasts with eyes and instruments directed at the sky. April 13th, 2029 is already marked in red on every planetary defense calendar. On this day, the office will fly just 32,000 kilometers from the Earth's surface, closer than many communication satellites, and will be visible to the naked eye as it streaks across the sky. For many years, the office has been the subject of headlines about the end of the world, the so-called planetary killer, first mentioned in 2004. However, since then, the threat of collision has weakened, giving way to a rare scientific opportunity, a live rehearsal of planetary defense as the whole world watches and the instruments are ready. A close approach is not just a spectacle. The gravity of the Earth will reach out to the asteroid, raising not water, but stone and dust tides. Scientists expect to see real changes, landslides on the surface, oscillating regoliths, and even changes in the silhouette of the asteroid. These tidal effects have never been measured on such a large object up close. This is a natural experiment that cannot be conducted in a laboratory. To observe it, NASA sent the OSIRIS-APEX spacecraft, tasked with meeting the office shortly after its flyby. His mission is to document every scratch, every moved stone, every shadow of the invisible pull of the Earth. Comparative shots before and after will show how asteroids react to close encounters, and how small gravitational nudges can alter the trajectory of a wandering rock. For Andre Riley, a systems engineer from the HERA team, this approach is personally significant. In her journal entry from 2020 to 2023, she recalls the anxiety she felt watching the dominance of the office in the news during her teenage years. This feeling of fear, softened by the promise of new technologies, now inspires her work. The office is more than just a test for scientists and spacecraft. This is a dress rehearsal for humanity's ability to track, model, and if ever necessary, deflect a real threat. Every calculation, every observation, every line of code written for OSIRIS-APEX or ground radar is a step towards a future where close encounters are perceived with precision and calmness, not panic. As the office rushes by, the world observes the workings of planetary defense, turning a headline once filled with fear into a story of readiness and discoveries. The Comet 3, I/Atlas, cataloged as C/2025 N1, stands out from the first spectrum. On July 1st, Pan-STARRS recorded its hyperbolic trajectory, but it was the chemical trail that hurried scientists to the world's largest telescopes. Data from the early VLTX, obtained when the comet crossed approximately 4.4 astronomical units, showed that the coma is dominated not by water vapor, but by carbon dioxide. JWST confirmed this data in August. The production of carbon dioxide is 129 kilograms per second, while water lags significantly at only 6.6. This ratio is almost 20 to 1, unmatched for such a bright and active comet. In contrast, most comets in the solar system have the opposite ratio, where the release of water significantly exceeds carbon dioxide. Here, the usual rules are turned upside down. Anomalies are not limited to just volatile substances. High-resolution spectra from the UVE-VLT instrument, captured over several nights in July and August, recorded a strong signal of atomic nickel, 4.6 grams per second, emanating from the coma on August 21st. However, the iron that almost always accompanies nickel in cometary chemistry was absent, having dropped below the detection level. This fact, the absence of iron in the presence of nickel, is extremely rare, even among interstellar objects. In the comets of the solar system, nickel and iron are usually found together, released as a result of the same heating processes. Theories range from unique formation chemistry to selective loss of iron over billions of years as comets drift between stars. Some researchers point to the decomposition of organic compounds rich in nickel, while others highlight the impact of cosmic rays that remove more volatile iron compounds. No model explains all the data yet, but the discussion is passionate and ongoing. Mid-August brought another surprise. The Martian Reconnaissance Orbiter, scanning ultraviolet wavelengths, detected a sudden flare, a flash that doubled the brightness of the comet in less than 36 hours. Ground photometry showed that the tails split into several components, with dust particles moving in different directions. These episodic bursts do not correspond to ordinary water streams. Rather, they hint at the emissions of carbon dioxide or other volatile substances when sunlight penetrates fresh cracks. Studies of rotation add mysteries. The analysis of the brightness curve suggests a slowly rotating, possibly oscillating core, spinning around an axis that changes over time. The rotation period exceeds 22 hours with only minor changes in brightness, indicating an almost spherical shape or complex rotation around a minor axis. This significantly complicates the prediction of outbursts and the evolution of the tail. Each new dataset adds another layer of intrigue, and with the perihelion set for October 29th, world spectroscopists compete to capture every detail before the comet disappears behind the sun. Currently, the I/Atlas remains a chemical anomaly, a slowly rotating messenger from a cold and dark corner of the galaxy.